All right, so welcome to another CCEM webinar. This is the second part of my FIB webinar. In the first part, I covered an introduction to FIB theory and the functions and mechanisms of the various FIB components. I hope you've seen that webinar because I do reference it in this one, and I assume that you've learned most of the contents there. But if not, don't worry. As long as you know a little bit about FIB, you'll be fine to understand most of this presentation. However, if you are from the future and currently watching this video on YouTube, then I do recommend that you see part one. This second part is about the most common FIB applications, and a few others too. I'll explain what they are and how to actually do it with some examples and tips. I'm trying to be brand neutral here, so this presentation can apply to any FIB operator. This means I'm not getting into optimizing for specific FIB models, but as a user, keep in mind you should adjust your methods to the designs and quirks of the particular microscope that you're using. Okay, let's begin. Not there. Let's begin here. Now we can apply what we've learned about FIB from part one to actually do the useful things. Among them are all of these. So the first one, cross-section cuts. With a few basic steps, FIB can be applied to study cross-sections in SEM down to a depth of a few tens of microns. This is a quick way to measure the thickness of coatings and oxides and to observe subsurface features such as internal oxide or semiconductor device defects. You can also do X-ray spectroscopy on the cross-section face, but be aware of the relative location of the X-ray detector so that you can minimize the effect of the trench walls shadowing the characteristic X-rays. Here are the steps. If the top 100 nanometers from the surface is important to you, then you should do electron beam deposition first after selecting the location to protect the surface from the ion beam before even looking at it with the ion beam. Then tilt up to the ion position and do ion beam deposition of the protection layer. Next is rough trenching at high current towards the edge of the deposit, maybe a scaling down to a medium current step or two, depending on the situation. Then apply the slow, low current cleaning mill, finishing about halfway into the deposit width with just one pass through the shape to give you a great surface. In my example, I combined this with trenching there. Remember this example from part one, if you did see part one, it's an example of how redeposition eventually closes off your trench if it's too deep and too narrow. Notice how I haven't lost any width of the cross-section face from top down to its deepest part. I don't have that problem here because I use trapezoids instead of rectangles, even though my trench goes twice as deep as that example. You can see there's redeposition there along the all the three other side walls of my trench, but it's out of the way. Okay, so the FIB work is done. Now adjust your SEM conditions for high resolution imaging and start snapping those images. Don't forget to apply tilt correction here to stretch the SEM image in the Y direction so that it's accurate in the vertical measurements. For height measurements of vertical cross sections, the tilt correction angle is 90 degrees minus the stage tilt. Sample preparation for the transmission electron microscope. This is the most common FIB task, and we do a lot of it here at the CCEM. A site-specific feature is chosen in SEM that's isolated, extracted, and thinned down to the 20 to 100 nanometer range. I'll describe the key steps. You might think this is all standard procedure, but it seems like every FIB operator has their own ways of doing things. My method doesn't seem to be the most common method, but I think it's optimized for my customers and my particular FIB. So you might see something different from the procedures that you were taught, unless you're one of my students. This doesn't mean that one of us is wrong. Keep that in mind. There are many ways of achieving the same thing, but on the other hand, I've seen many images online of kind of bad looking samples, so maybe not all methods are equal. So here are the steps. With the precision of SEM, you find the exact feature that you want to study in TEM. With that choice made, the procedure starts with the deposition of the protection layer. Again, start with electron beam deposition if needed. This is done at 0 degree stage tilt and coincidence height. and then switch to ion beam deposition at the 52 or 54 degree, depending on your microscope, coincidence height for the remaining majority of the coating. The target coating thickness depends on the material involved, how deep the sample needs to be, the microscope itself, and the precision of the probe alignments even. And the choices that the operator makes throughout the process also have an effect. Having a thicker coating than you ended up needing is always going to be a better option than finding out near the end of the whole full day of FIB work that you should have spent 5 more minutes on a thicker coating. So as a general rule with FIB, you should always err on the side of caution and quality rather than speed. When you're new to FIB operation, that's really not the time to push the limits of time efficiency. When you are confident in your abilities and have a low failure rate, then you can worry about ways to shave off a few seconds from each step. Okay, the next step is trench milling using the ion beam at high currents to clear the material around the target location. For a typical TEM sample size, I would suggest using a few different steps of probe currents here, starting with the highest current possible and positioning the boxes as far forward as you can without the extended damage radius overlapping with the protection layer. Then step the currents down and get closer, eventually finishing with a probe that you can trust to be positioned close to the deposit. It's going to look like my example here for the cross-section cut, except on more sides. Although that only works for the microscope brands that can run different currents in one batch of shapes, so others will require separate steps for each current. Here I also made a little pocket for my manipulator on the right there so that I can attach it, because attaching to the protection layer can cause problems in thinning behavior and other things. And attaching to a shoulder at the top means you had to extend over the huge mill boxes on both sides to make that extra space, which adds more time than it does to just add that little pocket. Some operators continue thinning the sample while it's in the trench there. I don't recommend it. So after trenching, we tilt back to 0 degrees for the lift out. Once there at coincidence height, insert the manipulator needle, bring it close, insert the gas nozzle, then carefully touch the needle to the lamella. When it's shaped like this, people call it a lamella. Then deposit a patch to attach the needle to the lamella, then cut the lamella out of the trench with the ion beam, lift it out with the micro manipulator controls. Careful not to touch the walls. Like an operation, that wishbone is the worst. The most common resting place is a copper 3mm half circle with posts in the middle. That's where we put it, and this fits a standard TEM sample holder. It's typically called a FIB grid, even though there's no grid, but that's language borrowed from other copper TEM samples that hold particles. Anyway, the lamella is attached by deposition to the post of the FIB grid on one side. I also rotate the stage to deposit on the other side too for extra strength. I've seen that not everyone in the world seems to do this on both sides, but I don't want the sample breaking off when someone drops the grid, so I spend the extra 5 minutes. Thinning is next. Most people are taught to use a mill box and just plow through the whole sample depth with it. My sample prep differs from most because I leave a thick frame all the way around the sample on 3 sides for structural stability. I do this by thinning with a line rather than a box. And I advance the line forward or backwards depending on what I see while watching the milling live with SEM. Admittedly, this technique is a little slower, but gives you far more instantaneous control over the milling. It enables you to keep the frame on the bottom more effectively, and it also minimizes redeposition. The ion beam is slightly over tilted when thinning from being parallel to the sample face, and this helps the thin lamella actually become more parallel. The ideal over tilt angle, it's microscope dependent and material dependent, but it's going to be around 1 degree. Okay, the thinning is done using progressively smaller ion beam currents and applied to both sides. The stage is rotated 180 degrees when switching sides so that I can always see the side that I'm actively milling in SEM. Never mill blindly. How far to push the thinning depends on the material and the needs of the sample. So if the researcher is doing HRTEM and EELs, then they usually want it extremely thin. But if they're doing EDS or looking for dislocations or doing TEM tomography, then it's better to be on the thicker side. So make sure you know what is needed. When the sample is almost thin enough, it's time to bring in the closing picture. This is a reference to part 1. So we're switching to low voltage. Remember what I said in part 1 about the penetration depth versus voltage. The two surfaces of the TEM sample will have gallium implantation, crystallographic defects, and some amorphization. In transmission, you're unfortunately seeing the additive effects of those on both surfaces. The inner core of the lamella is still pristine though, and we want the sample to be a little thinner and a lot less damaged after moving through the low voltage steps. In the final cleaning step, the sample is tilted back a few degrees, it's about 7 to 10, and the FIB is set to a somewhat low voltage. I start at 10 kV because the lower voltages are just too slow. At this glancing angle, the view from the FIB is the backside of the sample from what you're seeing in SEM. And remember, it's only tilted about 7 degrees, so the Y direction really goes a long way. A FIB raster box is placed only on the thin window area, and the ion beam just scans over that shape, slowly thinning it for a couple minutes on each side while I watch the progress in SEM, then rotate the stage and repeat on the other side. For HRTEM, 10 kV isn't quite good enough. We still want less damage, so drop the voltage to 5 kV and do it again on both sides. After that, it's usually fine, but you can go lower, especially on newer FIBs. They tend to have better optics at lower voltage. You could do 3 kV, even 2 or 1. The sputter rate, though, is going to be quite low, but if you've done the previous steps for a long enough time, then you only need to remove a few nanometers when you're down to the very low voltages to really get to that sweet innards of the sample where the crystal is untouched by the ion beam damage. So the damaged portion becomes a small fraction of the total thickness, resulting in a great HRTEM sample, ideally. Things can still go horribly wrong at this step, and you can wreck a sample right at the end if it starts to warp too much and forms rapidly growing holes. So good luck. Next, I'll present some options for TEM liftouts. Multiple windows. Now this isn't always going to be the best approach, but if the researcher only needs a small area because the sample doesn't change much, or they only care about really high magnification HRTEM, then a multiple window liftout is a good option. Instead of one wide thin area, it's possible to leave a thick bar or two in the middle of the lamella for more structural support. This gives you 2 or 3 narrower and independent TEM windows. The risk of sample warping is a lot less, and if it does, it's usually more manageable to deal with. Maybe only one side is bad and the other one's still good. This method also enables each window to be a different thickness, which is great if in TEM the researcher wants to have an extremely thin sample to do EELs, but then they also want to do EDS or electron diffraction with a thicker sample, or maybe look for dislocations. So with this method, you can have it both ways. Another trick is that the TEM windows don't even have to be in the same plane. So if you have a sample that has 2 or more offset features in the Y direction, like you might find in a semiconductor device, you can effectively make 2 different TEM samples in one sample. Hacks. Surface plane liftouts. Sometimes people want their liftouts extracted from a different orientation than by the typical cross-section. This surface plane liftout orientation is especially useful for studying crack tips or for extracting specific subsurface features deep within a sample that have already been cross-sectioned. There are a few ways to do this. The sample starts out with the target area laying flat 90 degrees to the typical TEM liftout lamella. And here the FIB needs to remove all the material under the target and just leave a small part of it attached to the side. This flat piece can be lifted out, but somehow it needs to be rotated up 90 degrees to be oriented properly for thinning. And this here is the key step that enables the whole process. There are a few ways to do this. If the micromanipulator can rotate, then you can use that feature. However, the rotation axis is probably the axial direction of the needle and not the tilt axis of the stage, so some gymnastics are required to make that work. A very effective method is to just find a way to hold the FIB grid horizontally, then attach the horizontal sample to the horizontal FIB grid. Next, you remove the grid from the microscope and put it back in its typical vertical holder, and the transformation is complete. The one snag here is that you probably need to either custom make a holder or buy a special one. Even if you have a holder that holds an SEM stub at 90 degrees, which is somewhat common, the problem here is the coincidence height is usually quite close to the SEM pole piece, commonly 4 to 6 millimeters, and most FIB grid holders keep the grid in the center. That's a problem. When you put it on its side, the FIB grid often sits far too low, and you can't actually get it to the coincidence height because the SEM stub would hit the pole piece first. If you can machine a grid holder stub to be nearly flat on one side, then you've solved the problem. This is one that I designed, and I had our mechanical guru technician, Andy, make the modifications, and it works very well. So I recommend something like that. Soft materials or very thermally sensitive materials can be easily damaged by ion beams or even electron beams. They may decompose, melt, heavily deform, or maybe the sample just has a phase transformation or some other reaction that you need to suppress. Many of these problems, though, will disappear if you make the sample very, very cold. FIBs can be equipped with a cryo stage to address these issues, and depending on the equipment, you may even be able to work with frozen liquids, for example, to prepare biological samples as close to their natural environment as possible without having to dehydrate them. I do cryo-FIB thinning, but there are a lot more challenges to overcome if the entire FIB process has to be cryo. And then even more if the sample needs to be inserted already frozen, removed frozen, and then transferred to the vacuum of TEM or atom probe or some other further instrument, all while still cryogenic. This requires very specialized equipment that's uncommon outside of a national level life sciences electron microscope facility. It's not our expertise here, not yet anyway, so I'm not going to go into any more detail, but cryofib for biology is a big topic worthy of its own webinar. All right, so another major use of FIB, especially here at the CCM, is preparation of samples for atom probe tomography. You can be forgiven if you don't know what atom probe tomography is because they're not as common as many of the other microscope techniques, and we have the only one in Canada. Our atom probe expert, Brian, already gave a webinar all about atom probes. If you're interested, you can find that on our CCEM YouTube channel. Here, I'll give an overview, very simplified, just one paragraph summary. So atom probe samples are cylindrical needles with a conical tip of nanoscale sharpness. In ultra-high vacuum, an electric field is applied to the needles with pulses of additional voltage or heat from a laser in order to provoke field emission of ions from the needle at known time intervals and measured times of flight to the detector. Combining the times of flight with the charge of the ions, a mass-to-charge histogram spectrum is collected, as well as the positional accuracy from the projection of the ion to the large detector. These data can be interpreted to create a 3D tomographic reconstruction of the type and position of each atom in the collected volume of the original needle. And if that explanation was too dense, you can watch Brian's webinar, but all you need to know right now is that we use FIB to make the needles and give them that nanoscale sharpness. I'll describe the steps. The steps up to the lift out are very similar to TEM sample preparation with a few minor differences. The protection layer doesn't need to be anywhere near as tall because most of the time you want to remove it entirely right at the end. However, the region of interest is typically a little longer in order to make many needles from one extraction. The shape of the lift-out comes to a point at the bottom, and this is done to minimize the contact area between the lift-out and the pedestal that it will be placed on. So the metal deposit completely fills in the space such that any vertical lines go through the metal deposit. The end of the lift-out is attached by ion beam deposition to conical silicon pedestals, we call them posts. And then a FIB mill line is used to make a cut, leaving behind one small chunk on the post. This process is continued to populate multiple posts with chunks of the extracted material. Usually 4 to 6 is common, and this is because sometimes it takes multiple samples to contain the right feature, and also because the failure rate in atom probe samples is fairly high, since they can fracture quite unpredictably before enough data has actually been collected. Following the attachments is typically rotating the stage to fill in the other side of the sample with more ion beam deposition. Each populated post is thinned with the FIB scanning in concentric annular rings, excluding the center, to form a cylindrical shape. The milling starts from outer diameter and finishes at the inner diameter, sort of like spiraling inward. Just one pass or many passes to the shape will work, and applying a gradient or a 3D dose profile can also be used here for more optimization. Another shaping trick is to intentionally defocus the ion beam. The amount of parameters that are available for you to tune with this sort of milling shape really depends on the FIB software, and it can take some trial and error to optimize the process to coax it into the tip shape close to what you want it to be. Of course, you can select the ion beam current and may want to use progressively lower currents as the needle gets thinner, down to a diameter of roughly 200 nanometers, where you'll switch to another technique. As with TEM prep, there is a low voltage final step here that is just rastering the beam over the entire needle with a fast dwell time. This removes the ion beam damaged outer layer, intentionally removes the protective coating, provides additional thinning, sharpens the tip of the needle into a nanoscale cone, and brings the tip down the axis of the needle to the target position in the Z direction for atom probe. For example, if you want to study a phase boundary, you may want the tip of the needle to be located maybe 100 nanometers above that boundary to ensure that your data set passes through it before the tip becomes too blunt for safe evaporation field. Sort of a tangent, but here's an explanation of why a lift out with a flat base wouldn't work. For this geometry, the deposit pads would be on the sides, as in the left image. So when it sharpens, the deposits would be milled away and there'd be no longer anything strongly holding the sample to the silicon pedestal. Even if this does happen to stay intact throughout the whole FIB process, the high voltage electric field in the atom probe would probably fracture it off immediately. So compared to the wedge method on the right, where there's always going to be the deposit layer between the sample and the post, that's clearly the superior method. Remember that surface plane lift out for TEM. There's a version of it for atom probe too. We use it a lot on samples that have a vertical boundary, like a grain boundary or a cross-section sample that goes through a phase boundary. Here's an example with a phase boundary interface in decarburized steel between the martensite and ferrite phase. This is a nearly vertical boundary. If you imagine making a standard needle from that, the boundary would run roughly parallel to the needle axis. If the two phases have different evaporation field characteristics, the tip shape might get a little weird with preferential evaporation on one side. Also for the FIB prep, when the needle is very thin, just a slight shift in the annular milling position or a slight wandering of the grain boundary itself could easily move that boundary entirely out of the needle, leaving a sample that only contains one phase, which is going to be useless. If the boundary could instead be forced into the horizontal orientation in the needle, then you no longer need to worry about the precise X and Y position of the needle because the boundary goes through every possible vertical line. The required precision is then reduced only to the Z direction, which means the proper placement of the final needle tip needs to be slightly above the boundary. To accomplish this, a 90-degree rotation is needed, and it's similar to the TEM surface plane liftout method, except the grain boundary isn't usually exactly vertical. This means that the ideal rotation might end up being more like 70 or 80 degrees, so you may need to check the side with FIB with a FIB cut to confirm the angle before you take out the sample and rotate it. And because of that, since we need to have the flexibility to select any angle, a fixed 90-degree holder isn't good enough. The solution we've developed here is to make a holder for a horizontal needle that also allows us the freedom to rotate the needle when we take it out of the FIB. So instead of attaching lift out directly to the silicon post, we first attach it to a horizontal needle temporarily. Then take the needle holder out of the FIB, rotate it the 70 degrees or whatever, and then put it back in. Following that, we need to deposit a new protection layer on top and then trim the lift out to the typical triangular prism bottom. From there, everything becomes the same as a typical atom probe sample. Another added difficulty of boundary samples is that when the needle gets very thin, the contrast often disappears. And so it becomes very difficult to continue tracking an important feature like a grain or phase boundary. But tracking is essential to know where to stop the low voltage tip descent. If you're lucky, what you can do is use a transmission Kikuchi diffraction detector or a stem detector. Those are very helpful for this, to see the grain boundary when you otherwise can't with regular SEM. But they're not mandatory. We do fine without them, but there's certainly less certainty when you're working nearly blind like that. The next major application is 3D FIB tomography. Now this could be a whole webinar itself, and it nearly will be because there are plans for future webinar on plasma FIB and 3D FIB tomography by Hui Yuan. So I'm just going to introduce the topic here, and I'll be fairly shallow with the details. Okay, remember the cross-section trench cut. First thing I introduced here. After our first image capture, what if we then take that cross-section and mill a tiny bit farther forward, like 10 nanometers, and take another SEM image, and then repeat 1,000 times? What we would get is a stack of images that stretches 10 microns deep, and when compiled together with software, they can be reconstructed into an interactive 3D tomographic volume. This technique overall is 3D FIB tomography, and the FIB-specific portion of it is often referred to as serial sectioning. Some people call it slice and view, but that's just the name of the acquisition software from one of the major FIB brands. Fortunately, we have the assistance of automation to do the 1,000 repeats of incremental milling and SEM imaging for us, because this process takes many hours, typically overnight or even over a weekend. However, it requires a lot of careful setup and some monitoring of the whole process to make sure that it's running smoothly. Things can go wrong, even hours into the run. The exact way to prepare a region for FIB tomography will depend heavily on the software, especially how it's designed to track features. The general setup, though, is that you need a protection layer to cover the top of the selected volume. You need a wide and deep trench in front that has enough space to keep redeposition from interfering with the milling and the SEM imaging. You need the cross-section surface to be clean, but it doesn't have to be flawless because you can expect to discard the first half hour or so of image slices since the run usually takes some time to stabilize. Hopefully the run reaches a condition where the drift is minimal and the automation functions are running smoothly. That's bare minimum setup here, but there are other common steps to improve the performance. It's common to also clear the left and right side of the tomography volume to further minimize redeposition effects and the gradual shadowing that develops in the electron image as the section face moves inward. However, some acquisition software systems recommend a very wide starting trench instead, which when combined with a wide milling front will usually work well too. Another typical procedure is the creation of high contrast markers that can be used by the software's image recognition features for alignment purposes. They're typically called fiducials. Often they're just a big X milled into the material or maybe milled into a nearby ion beam deposited pad that could give extra contrast if you do it that way. Some software uses markers within the tomography volume for tracking. For example, you can have diagonal lines buried in the top protection pad that converge from start to finish. The software can measure the distance between the marks on each subsequent image to calculate how far forward an image is positioned from the previous image. This is actually the slice thickness. And the number varies throughout the run from your target because of sample drifting, but it typically fluctuates around the chosen slice thickness target. These markers are enabled by using, in this case, carbon deposition for dark and tungsten or platinum for bright to create high contrast between the two materials. Another important feature is autofocusing and autoastigmatism correction. Some software will directly attempt to use the contrast features that are in your SEM imaging region itself, but that can cause artifacts such as dark carbon boxes or even beam damage and charging issues in some samples. I prefer the autocorrection region to be slightly outside of the image box for those reasons. Some systems use another set of markers for this that are again milled into the protection layer. The image on the right shows what they look like in the cross-section, and if the software is smart, it only needs to scan within those small boxes a few times to make these corrections. Is a diagram of all the features in preparation for serial sectioning. Note the box for the target image area. Since the SEM imaging is very time-consuming in the whole process of FIB tomography, it's ideal that the acquisition software allows you to select the region of interest for high-resolution imaging without having to scan or image the whole frame. This example is from a nickel alloy 600 after heat treatment. The boulders on the top are nickel metal nodules that were pushed out during oxidation, which is mostly internal oxide. And there are deeply penetrating grain boundary oxides here too. So the region of interest was along the grain boundary. This is the end result of FIB tomography after processing the whole image stack through reconstruction software. You get a block that can be rotated in 3D and sliced or cropped at any angle, but really that's just the beginning. By segmenting out the various features of the material based on the gray levels, shape, size, or other trends, you can take analysis to the next level. If you get there, you can apply all sorts of statistical analysis in 3D to quantify various features and identify ways in which different features interact or change across the volume. You can visually isolate or remove features to highlight the more interesting parts, again in 3D. But it's not so easy to get there. If you attended our online image processing workshop, then you'd be aware of the complexity involved in image segmentation and how modern approaches utilize deep learning tools. And if you can get over the huge learning curve of those techniques, then they can make your life a whole lot easier if you're doing a lot of FIB tomography. By the way, the lectures from that workshop are on our YouTube channel if you're interested in seeing them. As for what was learned from this particular sample, this is a massive oversimplification, but the resulting 3D tomogram in concordance with other characterization techniques showed that diffusion during the heat exposures induces a wavy grain boundary migration. Combined with chromium carbides pinning the boundaries, the resulting internal oxide depth was highly variable. In this case, the conclusions about the material and heat treatment would not have been recognized from just a TEM sample because a 2D slice really is insufficient to capture the full story of what's actually going on here in 3D. I should also mention that in addition to imaging of each slice, recent advances in the field have come from adding spectroscopy to the mix. So you can do 3D EBSD or 3D EDS. Also, plasma FIB allows huge volumes of material to be milled quickly, which has enabled a much larger practical length scale for 3D FIB tomography. We have one of those, but as I said earlier, that's a topic for another webinar. Okay, another application. Micromechanical testing structures is a creative and unconventional use of FIB. In this example, I've made cantilevers for the purpose of strength testing grain boundaries by using a nano indenter to apply the force. It looks a lot like the preparation of an atom probe lift-out, actually, except the dimensions have to be fairly precise and repeatable so that each beam deforms under the same conditions. It's hard to see, but there's actually a grain boundary at the start of each cantilever. And I think the idea was to push on it until that boundary fractures, which should happen before the cantilever bends down low enough to contact the bottom. It's also important to mill deep enough to prevent that possibility and to prevent the possibility of the indenter tip contacting the walls. Next, I have a cylindrical pillar where the surroundings were milled away to leave behind the pillar in the center. This application is also somewhat similar to atom probe. It's a larger version of the annular milling step, and like the cantilevers, each pillar should look identical, ideally. The researcher usually wants vertical walls, which is hard, but finishing with low currents, you can get close to vertical. The pillar can be used for compression testing of individual grains, again with an indenter. And if you do EBSD before the FIB, you could even find grains of specific crystallographic orientation to be chosen for the pillar locations. So pro tip, this could be a great way to study anisotropic material or slip systems, for example. I should also mention that there are more possibilities than just these two structures for micromechanical testing using FIB. And there's probably still room in the field to create new creative configurations to do this. Okay, let's talk about patterning. Images, text, or arrays of shapes can be etched into a surface using FIB. Similarly, ion beam deposition could also be applied beyond the simple rectangle. Some software can enable the creation of complicated arrays of shapes, and you can also apply 3D dose profiles to shapes, which can be used to finely control relative milling depths. You can import graphics, even vector graphics or CAD drawings. Here's an example of an array created by a former student here on the left. They are sub-wavelength bow ties for optical waveguide applications, basically for light polarization. The other image on the right is a microfluidics pattern, but there are many other applications of FIB patterning, and the field is expanding as newer generations and types of FIBs open up the doors to patterning at both larger and smaller than typical length scales. A lot of this comes from just changing the ion source to different elements. FIB can be applied for electrical applications. FIB deposition of, say, tungsten or platinum metal can be applied to connect device elements, but deposition of non-conductive material can also be used for isolation, as well as milling can be used to sever electrical connections. In this example on the left, I've deposited 2 tungsten pads to join device contacts to a pair of fused nanowires so that the researcher can test their electrical connection. Some companies make chips like this one here on the right, designed for electrical testing of FIB lift-outs. Additionally, very complicated circuit editing of microelectronic devices by FIB is possible, and this is usually used heavily by the semiconductor industry. It's enabled by software tools that can overlap the circuit schematics linked directly with the SEM imaging. They use gas-assisted etching techniques, and they have ways to stop the milling at the precise moment that a specific layer is exposed. This is called endpoint detection. Circuit editing, though, is not common in an academic facility. And this topic could be a whole webinar itself. Actually, I've seen one, but I'll leave it there. If you have a creative mind, you might have wondered whether FIB can be used artistically. Yes, it can. But usually we're busy using the FIB for science, so it's quite uncommon beyond people milling their university logo into their sample. But using much of the same techniques that I've already explained here today, FIB can be used to make microsculptures. I've done it before, the media loves it, and in reality, I think it's an underexplored use of FIB. Pretty much anything you make will probably be the world's smallest of that thing. And here are a couple examples. For Canada's 150th birthday, I mounted a tiny flag into one branch of one letter on a Canadian penny. From the FIB operational perspective, it's basically just an annular milled micropillar in a large pit with a TEM-sized lift-out attached to it and then a flag pattern milled into it. You just have to be very careful with images to get the right aspect ratio when you're not milling perpendicularly. And make sure to use a low current to get sharp edges when you're milling graphics or text. In December last year, I made this tiny gingerbread house to the disappointment of some purists who were upset that it's made of silicon and not cookies. Anyway, the footprint of the house is 10 by 6 microns. Oh, and it was built on top of a snowman because I can. This microsculpture was internationally viral. It was on nearly every news outlet. I showed the construction video in my last webinar, so I won't repeat that here, but it's on our YouTube channel. I'll talk briefly about some of the FIB process in the construction. So first, lifting and stacking large spheres is actually really hard. It helps to trim them a little, but still the deposition has a lot of trouble getting under deeply curved spaces. The house took a lot of planning to establish the size of the walls, determine the optimal construction order, how to do the roof pieces, how to make all 6 panels from one lift-out pit, and to nail the exact dimensions for each piece. The patterning part, though, isn't too difficult, but there are some hurdles. The vertical walls are done upside down and at an odd angle, so the image needs to be squished a little bit in the Y direction to fix the aspect ratio. It's also essential, as I mentioned, to use low currents to do sharp submicron patterning, and that makes the process take a long time. However, it's still fast enough that there's no room for error, because once the pattern starts milling, there's no way to undo what's been done. And if you find that the current or milling time or the position weren't perfect, too bad, you're stuck with it. All right, well, I'm going to finish up here, but if you are inspired to do something really cool with FIB, please send it to me. I want to see it. If you're looking for more in-depth information to learn about FIB applications, you might want to look up these resources. So thanks for joining us in another webinar. You can find all of our previous topics on the YouTube channel. Just search Canadian Centre for Electron Microscopy and it will come up. This series will continue. The next 4 topics are listed here at the bottom. They're about EDS, the Health Sciences Electron Microscope Facility for bio perspective, atom probe data processing, and preparation for EBSD. All right, it's question time. You can submit questions for me to the host in the chat box. And if we have leftovers by the time we're done here, I can do a follow-up Q&A video that will be posted on YouTube.
Great, thanks, Travis. So there's some questions that came in. And again, as Travis mentioned, if you have more questions, please feel free to put them in the chat. So the first question, what are the parameters you use for electron beam deposition?
Yeah, I went over this heavily in part 1, but there are a number of parameters. Actually, I can find that slide. Just give me a second. Right, here we go. Okay, so there's a lot of things to optimize for deposition. Things can go wrong. So there's an optimal current per deposit area. If your current is too low, the deposition goes too slow, and then you can have some incomplete deposition products from the precursor gas being trapped inside there. It's a waste of your time and a waste of the precursor gas. But then if the current's too high, you can get holes milling instead of deposit being grown, or the deposit can just be somewhat lumpy, uneven. So really there is a Goldilocks current. This is a delicate balance to maximize deposition rate or quality. Knowing what that is for your particular microscope is something I can't really tell you. It's going to depend on a lot of things, and as well as the size of the deposit, as I mentioned. But it's in the probably hundreds of picoamps current range. You also want to optimize for, there's dwell time, there's pixel spacing. The dwell time needs to be fast enough that the ion beam moves from the position right at the moment or before all the gas is depleted. Otherwise, after it's done depositing, there's no more gas to react with, so it will then start milling that area, and that's inefficient. There are more, okay, so the spacing of the pixels in the ion beam deposition matters. If they're too close together, you probably get depletion of the gas, and then you'll get some milling. If they're too far apart, you could get voids because the deposition is not going to be as tight as it should be. So there's a Goldilocks spacing as well. Really, it's best to just test an array of conditions, and you can figure out the best possible. Just spend like a few hours, and then you're good for the rest of your FIB life once you figure this out. As for dwell time, yeah, I mentioned there's an optimal for that too. And even you need to have a stop condition too, so to determine how far to go. This could be based on the time or the ion dose, or some software will try to estimate the total thickness. That's not a measurement though, it's sort of a hidden calculation based on an assumed deposition rate. So I prefer just to enter a time for the deposit, and once you've done a few of them, you have a good feel for how much that will give you. Okay, next question.
Same question, but can you make comments on electron beam deposition?
Yeah, okay, so for electron beam deposition, it is slow. So you only want to do that for as much as you need. And what you need is probably just enough to prevent the ion beam from damaging the material. The ion beam penetration depth if you're doing electron beam deposition of, well, let's say carbon, you probably want it to be over maybe at least 100 nanometers thick. And you want to make sure when you do the ion beam deposition on top that you're not milling first. So maybe start with a low current there as well. But optimizing it, you just want to blast it with the highest current possible, as long as your sample can handle that. That's really the most important thing. And don't go too high with the voltage. It tends not to work as well, unless you need to penetrate into pores or something like that. So a somewhat low voltage is good. As for dwell time, fast is probably better, but with some microscopes, there's sort of an inefficiency in when it switches positions, so you may actually get more net deposition by slowing it down a little bit. Okay.
What is the thickness of the sample when you start the 10 kV cleaning?
Yeah, that's a good question. It's going to depend on the needs of the sample. So if the sample is to be, well, it also depends on the material. If you really need to push the limits with the sample, then you don't want to start with, say, 150 nanometers or something and then expect to low kV mill that all the way down to 20 or 40 or something like that. If you have to do an excessive amount of low voltage cleaning, then you're going to get preferential etching, and that could be a problem if your sample's not a single crystal, and most of the time it's not. So the right thickness, well, you could base it off the depth of the amorphization and gallium implantation, and those are material dependent, but maybe before you've done the low voltage, after the 30 kV prep at low current, you're probably getting about 10 to 20 nanometers of damage on both sides of the lamella, and then that inner core is pristine. So let's say you wanted 40 nanometer thickness. If you start at 80 and then remove 20 nanometers from each side, you're probably good there. If you get too thin before doing the low voltage step, then you might not be able to sufficiently remove enough outer damage before the sample is too thin and you have to stop because of fear of it going horribly wrong and making giant holes. So typical good is probably 80 to 100 nanometers, somewhere around there, maybe a little more. It's going to depend, again, on how thick it needs to be in the end, but expect to leave about 20 nanometers on both sides to remove during this step.
Okay, during cryo lift out, is the needle also at cryo temperature?
As far as I know, it's not. Maybe there are some unique microscopes where that is possible. But cryo lift outs is also very difficult because you can't do deposition when it's cold. The precursor gas doesn't work. You just get a big mountain of the gas and won't be able to decompose it. So there are other strategies to thin samples without actually having to lift them with a manipulator, and those are typically going to work better for cryo. For biology samples, I think that's what's typically done, is they start with a cell or whatever the feature is on a TEM grid itself, and then do a really low angle, nearly parallel to the TEM lift out, make a lamella that way. You need sort of a pre-tilt stage in order to do that. But in doing that, you short circuit the whole deposition and lift out and attachment stuff. It's just milling, trenching, and thinning. So that's ideal. But yeah, I don't think I've heard of any system where the manipulator is cold.
Okay. How do you make sure the TEM lamella thickness is reached? Say, for example, 20 nanometers, because it's so difficult to image.
Yeah, so this is sort of by experience, because you can't really, at that point, the FIB image isn't going to give you anything useful. And even if you tilted back to 0 and tried to measure it with SEM, you're not going to measure very well at that scale. So what you do is rely on experience of looking at the image in an Everhart Thornley detector, because what you get there is when the electron beam goes through both sides, when it's thin enough, secondary electrons will be produced not only from the front side, but also the back side. And those will also be attracted to the Everhart-Thornley detector. And in that situation, the sample begins to look like it's glowing. There's sort of like a doubling of the brightness in the areas where it's thin enough. And as the sample gets thinner, the lamella with that detector gets brighter. And this effect is increased when you increase the voltage. But at some point, you'll see it's all white, and you'll need to step down the voltage in order to continue seeing contrast in there. So what I do is usually work around 5 kV for most of the thinning, and then by the time it gets thin, it's going to depend on the material too, but you see it start to get brighter. And then when it gets really bright, I may step down to 4 kV and start imaging there and watch it get brighter and try to make sure it's thinning evenly, and then step down to even 3 kV. And usually you don't need to go lower than that. And again, material dependent, but you just hit a target sort of brightness with that voltage, one that you use regularly, and you'll get a feel for it. But very heavily material dependent, like heavy metals like steel or something do not get as bright as other lighter elements like silicon, aluminum, or carbon, even at same thickness. So you have to be mindful of the material you're using as well. Okay, next.
Okay. Can you comment on the practical aspect ratios of the milled features in patterning with the ion beam?
I assume this is not XY, but it's more like XY versus Z, like how deep you can mill.
Yeah, I believe, yeah, that's
Okay. Yeah, so if you want to go deeper, a lower current is probably going to work better. That will give you sharper edge walls and allow more time for redeposited material to go out. But really, it's a problem to try to mill at too high of an aspect ratio, because there's that issue of redeposition closing off your bottom of the pit, and then you just can't mill any farther, because what you end up having is redeposited material lands back in nearly the same place from where it started, and you just keep milling that over and over and accomplish nothing. So eventually the bottom will come to a point and then stop. There are ways using gas-assisted deposition if you really need a very high aspect ratio. Sorry, gas-assisted etching with material gases like xenon difluoride. Using those, you can get deeper. But anyway, just test it first. I would say that's probably the best bet when doing something like patterning, is go to an area you don't care about and do a little test there and see how much you can get away with, and then transfer what you've learned to the good area.
Okay. What is the best spatial resolution achievable in the ion beam patterning?
Okay, so this is going to depend on your microscope and how perfect the alignments are. For my FIB's a bit old, so I don't think I would be able to mill a line with a width thinner than, say, 45 nanometers. Newer microscopes can do quite a bit better than that, gallium. Just probably more like, maybe they can be up to 30. If you want to get smaller than that, you have to go to a microscope that is no longer gallium, so a lighter element like neon or argon or even helium if you want to get really tiny. Then you can get, oh, we don't have one. I've never used one, but I think with something like helium, you could probably get well below 10 nanometers with an etched feature. And with other elements like argon and neon, it's probably in between, somewhere in between helium and gallium. It's maybe just a couple tens of nanometers. Any more?
Great. Nope, that's all the questions, Travis. So thank you for the great webinar, and thank you everyone for joining us.